welcome to my favorite Pasco experiment, the EX9918 diffraction of light. This experiment uses the Pasco optics bench, a linear translator, a diode laser, some slit accessories that have either a single slit or double slit configuration, an aperture bracket, light sensor, and a rotary motion sensor. Alright, so the first thing we'll need to do is mount the linear translator onto the optics bench, like so. Then what we want to do is we want to mount the rotary motion sensor onto the linear translator. So we undo that screw there, slide this on, the teeth go through the rotary motion sensor. And the linear translator has this bracket here, which you can tighten up to make a stop position so that the rotary motion sensor always returns back to the original position. And notice that I've removed the O-ring from the large pulley wheel. Then you'll want to remove this metal screw from the top of the pulley. And then you want to take the aperture bracket and the light sensor, and we'll mount these together like this. This assembly fits into the rotary motion sensor, like so, and then when you turn the wheel, the sensor translates linearly. Okay, and then we want to attach the sensor cable to the light sensor. And then we can connect the sensors to our 750 interface. And the usual yellow, black, and then an analog light sensor. You can do this with Passport as well. We're just using the Science Workshop interface today. And also notice the 750 is connecting to the computer using the USB serial converter. So now you take the diode laser, connect it to the optics bench like that, and now we fire up the laser. Okay, so I want it to go into the opening of the light sensor there. So I usually pick one of the smaller settings, like either that hole or that setting there, and I use that to align the laser. Now to align the laser, the back of the laser has these adjustment screws here, so I can aim the beam along the X and Y axis. So what I want to do is I want to move the beam around until I get it right in that hole. Right about there. And using one of the slit accessory dials, you mount this in front of the laser so that when you change the dial, you get different patterns and then different slit widths. So now you can see that the laser is aimed into the barrel of the light sensor, but the diffraction pattern is off at an angle, and we'd like it to be level. So then what we need to do is do a little more adjustment on the slit accessory. This screw here allows us to loosen the dial so that we can rotate it, so that the diffraction pattern will be level with the linear translator. So now we can see that we have a diffraction pattern that's relatively level there. Then we want to take the aperture bracket and select an opening size. And then by moving the linear translator across the pattern, we'll be able to read the light intensity while the rotary motion sensor tracks the linear position. With this stop set over here, I can make sure that the light sensor will always return to a position that's outside the spread of the diffraction pattern. Also, another key element to this, setting up this experiment properly, is that you want the maximum distance you can get between the light sensor and the laser. The larger that distance is, the more the diffraction pattern will spread out. The diffraction pattern will be spread out wider, and that makes it a little easier to get really good data as you scan across the diffraction pattern. Alright, so we have a light sensor in channel A and our rotary motion sensor there connected to the digital port 1 and port 2. There's a few different things that need to be set up for this experiment in Data Studio, though you can use the EX configuration file for the diffraction of light experiment. So for the rotary motion sensor, we'll want to turn up the experiment sampling rate. We'll say to about 50. The measurement we want to make is not angular position. We need linear position there. And then I go over to the third tab. I want 1440 divisions per revolutions, and on my linear calibration I need the rack setting there. Over on the light sensor, I think it's pretty well set. We won't use voltage, and we'll leave the calibration alone. So the display for this experiment, we're going to make a graph of light intensity as a function of position. So I drag my rotary motion position data down to the time axis and release, and now I have light intensity versus position. Now you notice when you do that, the X scale is in terms of meters. So from 0 to 8 meters, and you know that's just way off scale. So you can kind of bring that out a little bit. And I'll maximize that graph and collect some data. On the light sensor, I'm going to change the gain to 100 because we're dealing with low light levels, and when the diffraction pattern gets spread out, a lot of the light is really faint, and this amplifies the ability for the light sensor to see those faint points of light. Alright, so we hit start on Data Studio, and then with the rotary motion sensor, slowly turn the dial. And there it is. We have a double slit diffraction pattern there. And using this data, you can go through and measure the distance between peak to minimum and calculate the wavelength of the laser with the other geometry of the system.